Hi you guys, it's Mr. Pincher again. Welcome back to part 2 of our video on chapter 5 on the Discrete-Time Fourier Transform. In this part of the video, we'll look at periodic signals and also we'll look at properties of the Discrete-Time Fourier Transform. So for the Fourier Transform for discrete-time periodic sequences, we're going to kind of follow the same method that we did in chapter 4. So I'm not going to go through the details. But basically, what we do is just kind of write out the sequence in terms of its Fourier series, and then take the Fourier transform of each term, term by term. So what we end up with is the result down here. And again, this is very similar to the result we got in chapter 4. So it might be worth reviewing some of that material here. But basically, for a, now we're dealing here, the difference between this video and the last one is we're dealing now with periodic sequences, sequences that repeat over and over. So for periodic sequence, we can represent the sequence as a Fourier series here, a complex Fourier series. So this is basically stuff from chapter 3 where we first learned this. Remember that, n, uppercase N, is the period of the sequence, x of n, and omega naught, which is equal to 2 pi over n, is called the fundamental frequency of the sequence. And this is basically expressed in terms of harmonics, which are just multiples of omega naught. So we have omega naught, 2 omega naught, 3 omega naught, and so forth. The Fourier coefficients, again, this is from chapter 3, are given by this result right here. And finally, to get the Fourier transform of x of n, which is given by x of j omega here, what we do is, this is the formal description of the Fourier transform, but what it consists of are a bunch of delta functions in frequency. And these delta functions are sitting at the harmonic frequencies, where, again, those are just multiples of omega naught, which is given right here. And these, furthermore, these delta functions are weighted by the Fourier coefficients a sub k, and also by a factor of 2 pi. So we'll see how this works out when we look at some examples. But this is, again, almost exactly the same results as we had in chapter 4. So, this is a little bit confusing again when you see all this for the first time. But what this is saying here is that, of course, in the time domain, we have some sequence x of n. And let's say it looks something like this. So x of n, here is a periodic sequence. Notice it repeats itself every n, every period. So here's one period, here's a second period, and a third period, and so forth. From this, we can calculate the Fourier series coefficients a sub k. And those are, let's say those are plotted here, something like this. What we do now to find the Fourier transform, x of j omega, at least how to find the magnitude part, is we take each of these values here and replace each of these with a delta function. So we have a spike, and the delta functions are weighted by 2 pi times the value of these Fourier coefficients here. All right, so this first one has a weight of 2 pi a naught, the next one 2 pi a1, where a1 is the value up here. The next one would be 2 pi a2, and a2 is this one here. And furthermore, these spikes here, or delta functions, are sitting at the harmonic frequencies of the periodic sequence. So in other words, the first one sits at 0, omega is 0. The next one, omega naught, where, remember, omega naught, here it is 2 pi over the period. And the next one is the next harmonic, 2 times omega naught. The next one, 3 times omega naught, so forth. So this is what the Fourier transform of this sequence would be, of this repeating or periodic sequence would be. I'm going to skip over this slide. This is, again, just sort of a shortcut version of how to derive the result. I did this in detail in chapter 4. You're welcome to look at this, but it really doesn't give us anything extra here. It's just a way to show and prove the results for the Fourier transform down here. So let's do something a little more practical here. Let's start looking at some examples of finding the Fourier transforms for some periodic sequences. So the first one we're going to do here is a real basic one. X of n is just equal to the cosine of some frequency, omega naught, times n. And so the way we're going to do this is again, we're going to find the Fourier coefficients using chapter 3. Okay, and so, again, we did this in chapter 4 as well for continuous time. Now we're doing it for discrete time. So, back in chapter 3, we found that x of n, when it's equal to cosine of omega naught n, we can write that as basically this is using Euler's formula. We're just expanding this out into complex exponentials here. And then we're going to use our results from this chapter where the synthesis equation here, and we can see that a of -1, the Fourier coefficient here is 1/2, and a1, the Fourier coefficient, actually these are kind of crisscrossed, but this a1 corresponds to this 1/2, this a of -1 corresponds to this half, this 1/2 here. So our two Fourier coefficients are both equal to 1/2. Okay, so this is a sub k. All right, now, we actually did this back in chapter 3. All right, so this is review here. If you're a little confused on what I just did here, you can look back in the chapter 3 lecture or in your textbook for that. But what we're going to do now is we're going to replace these here with delta functions. So notice we have these two Fourier coefficients, which have a value of 1/2. They become delta functions here, and remember we multiply this value by 2 pi. So 1/2 times 2 pi gives us a pi. And here's the other 1/2 times 2 pi gives us pi right here. And they sit at, they are sitting here at omega naught, because we can see that's the frequency there. So notice this delta function here is at omega naught. This one is at minus omega naught. And that really is it. That is the spectrum for the cosine function. Now notice these things keep repeating, every 2 pi radians, these two delta functions here repeat themselves over and over. This is just because when you have a frequency out here, it's the same as this frequency, all right? Because when you add 2 pi radians to an angle, you get the same angle. So this one here, omega naught, this one here would be omega naught plus 2 pi, this one would be omega naught plus 4 pi, etc., etc. Here's another example, the Fourier transform of a discrete time impulse train. So this is what the impulse train looks like. It's a sequence of impulses, and they're, in between the impulses there are a bunch of zeros. And so, they can be separated by any number here. The period is given by this uppercase n. So this would be n, this would be 2n, the next one would be at 3n, and so forth. To find the Fourier transform of this thing, we need to find the Fourier series coefficients first. We actually did this again back in chapter 3, so I'm not going to spend a lot of time on this right now, but from chapter 3, to find the Fourier coefficients, we plug basically the value of x of n into this formula right here, the summation, and of course x of n just has the value of 1, and by the way, we sum it over one period. So what ends up happening here is we can use x at 0 here, which of course is 1, and we've got here, let's see, x of n is non-zero only when n is 0. So this is the only place where x of n has a value. All these other values of n here, of lowercase n, return nothing. Okay, so we can force n right here, little n, to be 0, and x of n then is equal to 1. So what happens here is, all of this stuff kind of goes away. We end up with 1 here. That's x of 0 times e to the 0, which is also 1. And the only thing that remains then is this 1 over n out in front. So what this tells us is that all the Fourier coefficients have the same value of 1 over n. So, and again, we did this back in chapter 3, this particular example. What we're doing new now for this chapter is we're going to use these values of Fourier coefficients to calculate the Fourier transform x of j omega. So all we have to do is multiply each of these values, and they're all the same, 1 over n, by 2 pi. And so notice all these delta functions here have the same weight, 2 pi over n, all right? Because that's our, notice we have to take 2 pi here and multiply it by a sub k, and a sub k is equal to 1 over n. So we have 2 pi over n, and we have basically a train of impulses here in frequency. And remember again, these impulses here are occurring at the fundamental frequency and multiples of the fundamental frequency. In other words, omega naught, 2 omega naught, 3 omega naught, etc. These, of course, again, are the harmonic frequencies for this sequence. We can do a slight modification of our previous results. So if we take the previous result and let n equal 1, then what we end up with is the following sequence. It's just a constant value. And let's let the value, I guess I let it equal to some number, a here. Okay, so a could be equal to 5, for example. So from our previous slide, remember all the Fourier coefficients were equal to 1 over n. So in this case, our result, instead of, because this is not a 1 up here, it's actually a, we just multiply all the results by a. So we have a over n for our Fourier coefficient, but remember n here, which is the fundamental period, we set that equal to 1 because this thing repeats itself every tick of little n here. So a over 1, of course, is a. So we multiply these values of a sub k by 2 pi. So we have 2 pi a. That is the weight of these delta functions here. And again, the delta functions, remember, show up at wherever the fundamental frequency is and all of its multiples. So what is the fundamental frequency? Well, remember omega naught, the fundamental frequency of any periodic signal or sequence, is 2 pi over the period. But the period is 1. So the fundamental frequency is equal to 2 pi. So we have 0 here, the first one. The next one's at 2 pi, next one 4 pi, 6 pi, 8 pi, and so forth. And also, what this tells us here is that, remember, 0 frequency is the same as 2 pi, which is the same as 4 pi, because these are actually an angle in radians, right? 0 radians is no different than 2 pi radians, because we've gone all the way around the circle. So all of these frequency components correspond to 0 frequency. So what does that mean? Well, look at our signal up here. Our signal is not oscillating at all. It's just constant. Our signal, in other words, has 0 frequency. And so that's exactly what's showing up in the transform here. The spectrum of the signal is only showing up at 0, or 2 pi. Let's now turn to properties of the discrete time Fourier transform. And again, I should mention that your book, your textbook will explain many of the properties of the DTFT. I'm only going to go over a few of the ones that are the most important for us. So the first thing is just remember the following notation. Whenever we have a Fourier transform pair, on the left side here, this is the time domain version, so x of n is a sequence. And on the right side is the frequency domain version. This is the Fourier transform, x of j omega. So this little arrow here just means that these two are associated with each other because they are a Fourier transform pair. Okay, so linearity property says that if little x of n is associated with big X of j omega and little y of n is associated with big Y of j omega, then if we scale and add our x and y sequences together in time, then in the frequency domain, the transforms will also be scaled and added together accordingly. So that is the property of linearity. The time-shifting property is something that we're going to do quite often. We're going to use this for solving linear difference equations. So again, the derivation for this follows very closely with what we did in Chapter 4. So I won't go over the details, but basically you take the synthesis equation, all right, for the discrete time Fourier transform, and you replace n with n minus n naught. In other words, we're doing a time shift or a delay of n naught. So this n here becomes n minus n naught. And then you split apart, the two exponents here, and you regroup and compare it with the original synthesis equation up here. And what we get is a proof that if we have a signal that's delayed in time by n naught, then the transform of the signal is the same, x of j omega, but it's multiplied by this phase term out in front, e to the minus j omega n naught. And remember, n naught here is an integer, a number, that represents the amount of delay here. So if we take a signal x of n and delay it by, let's say x of n is this cosine function here, and if we delay it by 2, we're basically just shifting it over to the right in time by 2. Well, it's going to have the exact same Fourier transform that it had before it was delayed, except now it's going to be multiplied by this phase term, e to the minus j omega n naught. We'll do some, we'll see examples of this later. But basically, if you look at these two cosine functions in time, they're identical, except obviously one's shifted compared to the other. So you can think of that shift in terms of time, in terms of n, it's shifted over 2 ticks, or you can think of it's shifted in phase, and that's really what this term represents physically. So let's take a look at some time-shifting property examples, and these are useful ways to do some basic calculations here with Fourier transforms. So suppose we're given the signal x of n equals 2 times 1/3 of the n times u of n, and you're asked to find the Fourier transform of x of n minus 5, okay? So how do we do this? Well, we're going to use this time-shifting property. I've shown it right here again, so we can refer to it. So the trick is, don't worry about the minus 5 thing here. Just find the Fourier transform of x of n. So x of n, remember, from the previous part 1, we're going to use our result for this sequence right here. We have the number out in front is 2, so that's going to go on top. And remember, this number in parentheses, we called it a in the last video, so this is a to the n. So it's b, or 2, over 1 minus a times e to the minus j omega. So here's that 1/3, we put it in there. That's our value of a. Then we're going to apply the time shift property. So we have to take this transform, x of j omega, and all we have to do is multiply it by e to the minus j 5 omega. Now, where did that 5 come from? Because that's our delay right here, according to our time-shifting property. So we end up with, it's basically the same result here, but we multiply the top by e to the minus j 5 omega. That's that phase term. So here's our final answer here for the time-delayed version of x. Here's another one. Let's say it looks like x of n is the exact same sequence as up here. So this time we're asked to find the Fourier transform of x of n plus 2 instead of x of n minus 5. So again, everything goes exactly as before. You find x of j omega, it's the same as up here, no difference. And now our time, it's actually not a delay, it's an advance. We're moving everything to the left by 2. So, but we use the same time-shifting property. We're going to use this right up here. This time n naught is actually -2, so this term out in front becomes this right here, e to the positive j2 omega, and we multiply that times the 2 up on top to get our final Fourier transform, which is shown right here. Now here's one where we're going to work backwards. This is again going to use the time-shifting property. So suppose that we are given a Fourier transform that looks like this thing right here. 3 times e to the minus j2 omega over 1 plus 1/4 e to the minus j omega. And we're asked to find the inverse Fourier transform, or in other words, find the sequence y of n that has this as its transform. So what we can do here, at first glance, it might look a little bit, daunting, but actually, if we take the numerator, the stuff up on top here, and put it out in front, now we can see what's happening here. All right, we've got a 3 out in front, that's simple. But this term here, e to the minus j2 omega, that, remember, is from the time-shifting property. This causes a delay of 2. All right, well, that's where that 2 is right in there. And then the rest of this stuff, the 1 over 1 plus 1/4 e to the minus j omega, well, that's just a decaying exponential function. This is the one that we learned in the last video. So this sequence here would be negative 1/4, all right, because there's not a minus sign there, there's a plus sign. So it's negative 1/4 to the n times u of n. And remember, this term out in front here delays this thing by 2. So I'm going to put my 3, remember that was right here, this is the original 3 up here, that's out in front. We have minus 1/4, and then so we have n minus 2 times a step function u of n minus 2. The reason it's n minus 2 is because of this delay here. Here are a couple more examples. And by the way, these examples that I'm showing you now will help you with the homework and worksheet that goes with this chapter, because you're going to have to do some problems very similar to these. So in this one, you're asked to determine the Fourier transform of this sequence. So the sequence, it's a couple of delta functions. It's delta of n plus 3 times delta of n minus 2. And so the way to do this is, remember, the discrete time Fourier transform of a delta function is just 1. So this first term here, when we take the Fourier transform, that gives us a 1. The second one, we have 3 times the delta function. So that gives us a 3, but remember, this delta function is delayed by 2. And remember, the time shifting property means we pick up a delay term of e to the minus j2 omega. So we can multiply that by the 3, and here is our Fourier transform x of j omega for this sequence up here. And this next example here, we can work backwards. Suppose that we're given the following Fourier transform. Y of j omega is equal to 5 e to the j omega plus 2, and we're asked to find the, use the inverse Fourier transform to find the sequence y of n. All right, so again, let's do the easy part first. This second term here, this 2, just gives us 2 times a delta function, because remember, the Fourier transform of a delta function is 1. So this 2 here just means 2 times the delta function. And likewise, this 5 here is going to give us 5 times the delta function, but e to the j omega, that is using the time, remember, using the time shifting property, this gives us an advance of 1, not a delay, an advance, because there's not a minus sign in front of there. So this term here becomes 5 times delta of n plus 1. Let's take a look now at the frequency shifting property. And again, this is very similar to what we did in chapter 4, so I'm not going to go through the details here of the derivation. But one thing we're going to find out here is, just like we did in chapter 4, there's sort of a duality here between time and frequency. So this time, what we're doing is we're delaying or shifting the frequency of the transform by some amount omega naught. And what that does is, that means in the time domain, we have x of n, but we have this phase factor e to the j omega naught n. And omega naught here, this frequency here, that's the amount of frequency shift that we did over here in the transform. So, again, we'll end up with this part of the lecture with just this slide here that sort of points out this dual nature of the time and frequency shifting properties. So in time shifting, we delayed the signal in time, and it produces a phase term over here, e to the minus j omega n naught. For frequency shifting, what we're doing is we're shifting in frequency, we're shifting the transform by some amount omega naught, and that produces a phase term e to the j omega naught n in the time domain. So you can sort of see these two properties have a sort of duality to them. A time shift in time causes a phase shift in frequency, and a frequency shift causes a phase shift in time, conversely. So that is it for part 2 of this video lecture. I will see you again in part 3 later. Goodbye.